Okay, here's our first sample on Newton's second law for rotating objects. It's a simple pulley, part 1 on page 489. So we're going to start off without any numbers. We have a pulley with a mass M. I guess I'll use capital M since your book does. Radius R. Okay, so let's draw our pulley right here with a radius R. So it says we are exerting a force F on the outside with a rope. So here is our rope draped over the pulley, and we're assuming we're going to pull straight down. And in the next problems, we'll have a mass actually providing that force, which will be straight down. So we're looking for what is the angular acceleration of the pulley. Okay, so we're going to use our two ways we know to indicate torque to do this. So first of all, the definition, I guess, if you will, is RF sine theta. So for this, we can't do much but write down R for the radius, F for the force. So I've drawn here the vector R, right, which I should have put an arrow on. It doesn't really matter if the arrow goes this way or that way because the angle either way is 90 degrees. So that's maybe our first actual look at that. So I did draw that. The sine of 90 degrees is 1, so tau is just equal to RF. Okay, so that's our definition, if you will, of torque. But also our Newton's second law has another way to write torque, and that is tau equals I alpha. So what you know from algebra is that if this is equal to tau and if this is equal to tau, then those two things are equal to each other. So I'm going to go to the next page so I don't run out of room. RF equals I alpha, which really seems abstract at this point, but that's okay. I maybe should have done a capital R here so I could be consistent for you guys. So a pulley, and we're going to do a lot of pulleys. As far as I know, they always tell you that the moment of inertia for a pulley, which is essentially a cylindrical disc. It's a very, very thin or short cylinder, like we said. So the moment of inertia for that is 1/2 mr squared. So I can write that into our formula as well. So we have RF equals I, which is 1/2 mr squared times alpha. So solving for alpha, I get alpha is equal to 2 times, well, I won't skip steps, 2RF over mr squared. So we can cancel out one of the r's. So we get 2F over mr. I don't know why I don't know what's going on here. 2 alpha equals 2F over mr. Now, we can go ahead and circle that, but that doesn't mean much to you unless you actually think about it and unpack it. What do those things actually mean, okay? So, how do I get a larger angular acceleration? And remember, the angular acceleration is also tied to the linear acceleration of whatever's pulling, which we'll get to next time. To get a larger angular acceleration, okay, we need a bigger force. That should be pretty intuitive, right? If I pull harder, it's going to spin faster. Okay, fine. What about the mass, right? A smaller mass is going to result in a larger angular acceleration. That should also make sense. If my pulley doesn't weigh as much, it's not going to be as hard to rotate. So since the m is in the denominator there, what else is in the denominator? The radius. So to get a larger acceleration, I also need a smaller radius. And we've already we've definitely talked about how stuff that is tighter and compact is easier to rotate. So if I have a given force, a smaller radius is going to accelerate faster. So again, it could be very easy for you to just kind of plug and chug and write 2F over mr and move on to the next problem. But let's be honest, I'm not going to ask you to derive this on a test. I'm going to ask you questions like, how could I make it easier to spin this, right, if I have a given force? So in order to answer questions like that, you really have to look at this. And this is why we do questions like this without numbers. I could give you numbers and you could plug and chug, but that's not really how things work. It's not going to help you answer questions like, well, what happens if I double the mass? So that's our first pulley question. I'm sorry to say they get more difficult, so please make sure you understand this one before you move on to your next sample.